Greetings to everyone. We are going to have a session on eigenvalues and eigenvectors. In this session, we are going to understand about how linear transformation works and with the help of eigenvalues and eigenvectors using their principles and their properties. What are eigenvalues and eigenvectors? Generally, we perform operations and use matrix for applying eigenvalues and eigenvectors. For square matrix, eigenvector is a special vector that only gets scaled, not rotated when multiplied by a. This means eigenvector is a special vector that doesn't change its direction when it undergoes transformation. Other vectors may change its direction, but in case of eigenvectors, it doesn't change its direction even though after transformation. Hence, we use eigenvectors in our study case. Here we have equation AV is equals to lambda x. Here A is equals to matrix, the matrix we perform operation. V is eigenvector and eigenvalue. We have to know about eigenvalues also. Eigenvalues means we use eigenvalues for it tells that how the eigenvector is stretched or compressed after transformation or during transformation. Eigenvectors specifies that the whether the eigenvector we are using is stretched or compressed or rotated in the transformation. It completely tells about the transformation from one dimension to another dimension. When vector is transformed from one dimension to another dimension, these eigenvalues and eigenvectors are used. Have just look on how to find these. Finding eigenvalues and eigenvectors. We have a character equation by solving the previous equation. We can have a eigenvalues and eigenvectors equation that is known as characteristic equation. When we use this equation, we can solve any eigenvector or any eigenvalue get, and we can have an overlook on them. In 2 by 2 matrix, we have a matrix, and when we use a character equation to solve it, the rate of we are using a minus lambda, that is a characteristic equation. From applying this, we can get a quadratic form. By solving this, we can get what we want. For finding eigenvalues, by solving the previous equation what we have get, by doing performing row and matrix operation, we can get matrix lambda is equals to 2 and lambda is equals to 4. As we previously discussed, how we can tell that eigenvalues influence and tells about how eigenvector is stretched or compressed and how it has changed during the transformation. Hence, for example, when we got the eigenvalues lambda is equals to 2, when lambda is equals to 2, that is eigenvalue is equals to 2, we can tell eigenvector, that is by solving this. When we substitute lambda is equals to 2 in a characteristic equation to get the character vector, we can get that here v2 is equals to minus v1, so vector transforms into other dimension in negative phase. Eigenvalues and eigenvectors have special influence and have made a lot of contribution to the technology. So when we see a lower look on real world applications, we can in 3D graphics and scalings, that is using GPUs in computer graphics, eigenvectors determine principal axis of deformation. That means we can form 3D object by using scaling, rotation, sharing. Eigenvalues is called scaling factors along principles. As we discussed, eigenvalues influence That means tells about the how eigenvector has changed without how it is, as it has rotated or stretched, compressed, and also we can, but the special factor in eigenvector is it doesn't changes its direction even though after transformation. Hence we use eigenvectors, and eigenvectors influence. Hence we have got eigenvalues is equals to scaling factors along principal axis. Deformation analysis in skeletal animation. That means we can deform the equation we are having, and we can perform any scaling graphic. As we discussed, GPU computing, parallel processing means as we have CPU, it has GPU which performs eigensolver algorithms leverage GPU parallelism. In this processing, we have a principle eigensolver algorithms leverage GPU parallelism, means it performs large matrix eigen decomposition on GPUs. When we want something like when we compress or zoom in or zoom out some images, by beyond this process and principle we get that scientific computing eigenvalues low solves the quantum mechanics. It is one advantage of eigenvalues and eigenvectors. In machine learning, GPU accelerated PCA CVD operations. There are special operations. Image compression, as we discussed about image compression, that is zooming, zoom out, we use eigenvalues and eigenvectors. SVD, singular value decomposition using eigenvalues, compress image by keeping only significant eigenvalues. That means we have a topic called normalization. In this normalization means when as we transform one dimension to another dimension using eigenvalues and eigenvectors, that is we use eigenvalues and transform eigenvectors. By using this normalization we can transform eigenvectors but keeping its magnitude to 1, means it transform from one dimension to another dimension, but it have consist a unit length, that is magnitude, so we can save memory space, etc. That's the here principle. Compress images by keeping only significant eigenvalues, meaning is this. Reduce storage, that is one advantage. Retain 95% quality with 5% data. Video compression, facial recognition, data storage, these are major improvements. And also this is used in engineering and physics, as we can determine vibration analysis, natural frequencies is equals to eigenvalues. Structural engineering, principal stress directions, eigenvectors. Stability analysis, system stability of eigenvalue science. This is when we discuss about this, analysis means when scientists or engineering build a architect by using eigenvalues and eigenvectors performing operations. They check whether the system stability is perfect or it collapses when during any circumstance. So it has a system stability analysis, system able stability from eigenvalue science. And in quantum mechanics, energy levels is equals to eigenvalues, means using eigenvalues we can determine the energy levels. And as AI is improving rapidly, machine learning and PCA, principal component analysis, find its features. Eigenvectors is equals to principal direction in data. As we discussed, it compresses the data as performing normalization orthogonality operations. It acts as a principal direction in data. Eigenvalues, principal variance along each direction. As we discussed, it doesn't change direction. Dimensionality reduction for high dimensional data sets, as we discussed, normalization or and also have feature extraction for image and facial recognition. Key mathematical properties, symmetric matrices, all eigenvalues are real. Orthogonal eigenvectors from distinct eigenvalues. Orthogonal means 90. Sum of eigenvalues is equals to trace of matrix. This is the principle. Product of eigenvalues is represented as data. So we have a lot of uses using eigenvalues and eigenvectors. We have implemented in our technology too. So we can literally, when we talk about eigenvalues and eigenvectors, we can conclude that eigenvalues reveal scaling factors, eigenvectors show special directions, essential for graphics, physics, and machine learning. Power in GPU computing and compression. That means it's a basic principle and important for GPU. So that's all for this session. Thank you.